This program is brought to you by Stanford on iTunes U at Stanford University. Please visit us at itunes.stanford.edu.
The last time we had started to discuss charged particles moving in electric and magnetic fields and how relativity impacts the laws of charged particles in electric and magnetic fields. How the Lorentz force law, which is basically the law of how electric and magnetic fields influence charged particles, how that law and if that law is really consistent with the principles of relativity. Are the rules the same in every reference frame? And what are those rules? How do we have to modify the non-relativistic laws of motion in order to make them the same in every reference frame? And we do have to modify them, there's no question of that. F equals ma makes good sense in a world where acceleration is an invariant, and in Galileo's world or in Newton's world, everybody would agree about the acceleration of an object. Everybody would agree about the force on an object. Everybody would agree about the mass. And so F equals ma was an invariant equation that all observers would agree on. But there are kinematic changes, what we mean by velocity, what we mean by acceleration, and so forth. And so it's not surprising that the Newtonian laws of motion will have to be modified. Now, in particular, we're going to have to understand the concept of force and where forces, well, not so much where forces come from, but a deeper concept of force. There are many different kinds of forces in nature, and they tend to have different extensions from non-relativistic to relativistic physics. For example, the laws of motion of charged particles look off in, if you ignore completely magnetic effects incidentally are themselves relativistic effects. If the speed of light were infinite, there would be no magnetic force on charged particles. That's because the force on charged particles is proportional to the velocity, and whenever you see a velocity, you'll always know really it's a velocity divided by the speed of light. There would be no magnetic forces if the speed of light were infinite. There would only be electric forces. And the force laws, F equals ma, together with the Newton law of force. The Newton law of force looks suspiciously like the Coulomb law. Instead of products of charges, we have products of masses. They're both inverse square laws. The laws of motion for gravitation and for electric forces look very, very similar. You might expect that perhaps the generalization to the special theory of relativity would also look very similar, and you'd be wrong. They're very, very different. In fact, as I'm sure you know, the laws of gravitation don't naturally lend themselves to an extension in the special theory of relativity. It was necessary to go on to a more thorough modification of space-time for gravitation, but not so for electrical forces. So today we're going to go through the basic laws of electrical and magnetic forces on charged particles and the equations of motion. Let me just write down what they are, as Lorentz would have written them down. Just before, a few years before the discovery of the special theory of relativity, he of course would have used Newton's forces, and he would have said mass times acceleration. This is when he wasn't thinking so hard about the speed of light, when he was trying to be fairly conventional about electrodynamics. What he said, of course, was force equals mass times acceleration. By acceleration, he meant exactly what Newton meant by acceleration, the time derivative of the velocity, and by the velocity, he meant the time derivative of the position. All right, let's work on the left-hand side of this equation just for a moment. Mass is mass. Acceleration is the time derivative of the velocity. So let's write time derivative of velocity. Both are vectors, ordinary three-dimensional vectors. I won't bother indicating that. They're both three-dimensional vectors. And the mass of every object is time independent. The mass is simply a parameter that's identified with an object once and for all. It doesn't change with time. In relativity theory, the mass doesn't change with time because by definition, it's the mass when the object is at rest. In Newtonian physics, it's a deeper principle in Newtonian physics that mass doesn't change. But in any case, mass doesn't change with time. And so you can bring it inside the derivative, and you can write the right-hand side here as the time derivative of the mass times the velocity. And the mass times velocity is known as momentum. Always carries the symbol p. It's also a vector. And so we always write the right-hand side here as the time rate of change. I'll put a little vector symbol on it now, dp by dt. And that's equal to force. That's a fairly general definition of force. It actually transcends a little bit simple Newtonian physics. As we'll see, there's a version of it in general relativity. Sorry, in special relativity, even in general relativity, that the time rate of change is the force. But there's a slight difference in the definition or the connection between momentum and velocity in the special theory of relativity and in Newtonian physics. I'll just remind you, in both cases, the momentum is mass times velocity, but in the special theory of relativity, it's not ordinary velocity, but the time rate of change of position with respect to proper time, proper velocity. We'll come back to that. We'll come back to that. That's the left-hand side. Actually, it's the right-hand side of this equation. But now I'm going to put another right-hand side to the right of this. I'm going to write down the Lorentz force law. We're going to work, here's your homework. Your homework is to put all the speeds of light back into the equations by doing dimensional analysis. We are going to set c equal to 1. The non-relativistic limit, in this case, will not be the limit in which c goes to infinity. C is just 1. It's the limit in which the velocity gets very, very small. So if you want to think about what non-relativistic physics means, it means very small velocity. All right, what's the right-hand side here? Well, according to Lorentz, the right-hand side is proportional to the electric charge. Now we're talking about electric and magnetic forces. Proportional to the electric charge, which I'll call Q, of an object. And then there's one term which is electric field. The electric field is a vector. In general, it depends on position as well as time. It has a set of components. The components are three-dimensional components, x, y, and z. And then Lorentz discovered another term. It was actually implicit in Maxwell's work. It was implicit in Faraday's work. But Lorentz really spelled it out. And it's the velocity, the ordinary velocity cross product, and I'm going to explain that in a minute, cross product with the momentum. Oh, sorry, not momentum, B. Thank you. B. Cross product with the magnetic field. The magnetic field also being an object with components. It's also a vector in space, very much like the electric field, but it influences objects in a different way, be of also position and time. So in general, these fields are time-dependent and position-dependent. Okay. Now, the magnetic field, I've told you that it's a vector. First of all, I haven't told you what cross product means. So let's, most of you know what cross product is, but I want to think about it in a slightly different way than the usual concept of cross product. The cross product of two vectors you normally think of as another vector, and that other vector is perpendicular to the vectors which are being multiplied and proportional to the product of their magnitudes times the sine of the angle between them. That's not the way I'm going to think about the cross product. I'm going to use a definition of the cross product, in which the cross product is really a tensor. It's an anti-symmetric tensor that you make up out of two vectors. Now it's very easy to make up a tensor out of two vectors if I have two vectors A and B, and right now B is not the magnetic field. I just need two letters, so I'm going to call them A and B. If we have two vectors, I guess I should indicate that they are three-dimensional vectors by a little arrow over them, ordinary three-dimensional vectors. There's a notion of cross product, which itself is another vector, which I can call C. All right. There's another concept, as I said, of cross product, which makes it an anti-symmetric tensor. Here's the idea. You take any two vectors, and you can make a tensor out of it. A tensor is simply an object with two indices instead of one. Now, I'm thinking now about three-dimensional space. So a vector has three components. A tensor, in this case, has 9 components, 3 times 3. It's a matrix built up out of the components of the vector. So if the vector A has 3 components, incidentally, I will freely interchange between 1, 2, and 3 and x, y, and z. So x is 1, y is 2, z is 3. A has 3 components, B has 3 components. The cross product also has 3 components. But as we'll see in a moment, that leaves a little bit of an ambiguity. There are two objects in 3 dimensions which have 3 components. One of them, or 3 independent components. One of them is a vector and the other is an antisymmetric tensor. So given two vectors, we can always make a tensor. For example, we can make the tensor AM, M and N, remember mu and nu, go from 0 to 3, time and space. That's the notation I will use, I've been using. Things from the rear end of the Greek alphabet represent space-time indices. M's and N's, Latin letters, just go from 1 to 3. Ordinary space, ordinary spatial indices. All right? So if you like, a 4 vector has an index M, 1, 2, and 3, and also a 4th index 0. Okay, so AM, we're working now strictly in 3 dimensions, trying to get 3-dimensional space and ordinary vectors right. AM, we can take AM times BN. Right. That is a matrix whose components, if we wanted to work out the components, the 1, 1 component would be A1, B1. The 1, 2 component over here would be A1, B2, and then A1, B3. I won't write them all out, but here would be A2, B1, A2, B2, and so forth. 9 components altogether, 9 independent components. Now, as it stands, this is not an antisymmetric tensor. It's got no particular symmetry. There's no particular symmetry. A2B1 is not, there's no particular reason why A2B1 should be the same as A1B2. They're two quite different things. But if we subtract ANBM, in other words, we consider the tensor made by interchanging A and B. AMBN and ANBM, if we subtract them, then that gets rid of all the diagonal elements, A1B1 minus A1B1, and it's antisymmetric because it'll contain things like A1B2 minus A2B1. In the 1, 2 element, you can see that it's antisymmetric. If you interchange N and M, if you interchange rows and columns, the two terms will interchange, and so what we'll get is an antisymmetric tensor. The antisymmetric tensor has zeros off the diagonal. Right. It has, for example, in the place over here, not A1B2, but A1B2 minus A2B1. Let's make it a little bigger. A1B2 minus A2, B1. And then A1, B3 minus A3, B1, 0. We'll come back to that over there. Then down here, let's see, that's A1. What will we have here? A2, B3 minus A3, B2. And then 0. The diagonal elements are 0. There's off-diagonal elements here. And what about the elements below the diagonal? The elements below the diagonal are the same as the elements above the diagonal, except opposite in sign. So over here, you'll have A2, B1 minus A1, B2, which is simply the negative of its reflection about the diagonal. That means there are 3 and only 3 independent components of this antisymmetric tensor. Well, you can always put 3 components and you can line them up and call them the components of a vector. That doesn't mean that they transform properly as a vector, but these 3 objects do transform properly as a vector if we make the right identifications. In particular, those who know what a cross product is will already see the pattern that these are the components of the cross product of A cross B, but in particular I'll tell you which components they are. They are the components A1, B2, that's C3. Let's write it over here. No, let's do it over here. C3. This one is C3. 1, 2, 3. All right. What about this one? What would you put here? Temporarily, let's put C2 there. And this one, of course, would be C1. In other words, these 3 objects can be placed in one-to-one correspondence with the components of this antisymmetric tensor here. The antisymmetric tensor is one form of the cross product, which in fact generalizes to other dimensions. In other dimensions, an antisymmetric tensor will not have the same number of components as a vector. So this is special to 3 dimensions. In higher dimensions, there's no such thing as the cross product of 2 vectors giving another vector, but there always is the cross product giving an antisymmetric tensor. So the generalization of the cross product to other dimensions is the antisymmetric tensor. For 3 dimensions, it's fine to think of it as a vector. Now, it's actually C2 here. Let's write it out here. C3 is equal to A1, B2 minus A2, B1. Now, if we start cycling this equation, the trick is always to cycle through it, 1 to 2, 2 to 3, and 3 back to 1. C3, the next one, what comes after 3? 1. C1 equals A2, B3 minus A3, B2. And 3, the next one is 2, of course. There's only one left. All right, and this is 1, 2. This will be A3, 2, 3, B1 minus 2, 3, A1, B3, I think, right? Okay, now let's check. All right, what do we have? We have over here A1, B2 minus A2, B1. That's C3. I got that one right. Okay. C1 down here, that's A2, B3 minus A3, B2. But C2, my temporary identification, C2 as A1, B3, that's wrong. It's minus C2. Okay, you can see there that C2 is not A1, B3 minus A3, B1, but minus that. So in fact, what goes here is minus C2. So the components of a vector can always be displayed as an antisymmetric tensor, or the antisymmetric tensor can always be displayed as a vector. Now, what's going on here? What's the geometry of this? An antisymmetric tensor has two indices. Every component of it is associated with two axes, an x-axis and a y-axis. Okay? Well, the xy axis, the xy component of the antisymmetric tensor is simply identified with the z component of the vector. It's clear that it's ambiguous. Do you describe a vector by describing the plane that it's perpendicular to, in which case you're describing it by a pair of vectors, namely the pair of vectors that defines the plane, or do you describe it by the arrow that's sticking out of the plane? The two ways of describing the vector, one by just an arrow sticking out, is describing it by its vector components. The other way of describing it is in terms of the planes that are perpendicular to those vector components, and that's the description in terms of the antisymmetric tensor. Now, the difficult thing, it's not very difficult, it's rather easy, is to prove that the components of the antisymmetric tensor transform under rotations according to the same rule as the transformation properties of a vector, and they do. They do. So these are two different aspects, or two different ways of thinking about the three components of a vector in three dimensions. The cross product, and for many reasons, or for many purposes, it's smarter to think about the cross product as a tensor rather than a vector. But then again, in visualizing it and trying to get a picture of it in your head, you might want to flip back and forth between vector and antisymmetric tensor. Okay, that's the idea of a cross product. Now, let me do one more little exercise for you. Yeah, no, not an exercise yet. Let's come to the magnetic field. Now, the magnetic field is a vector, but it is also an antisymmetric tensor. Zero, B12, B13, B21, which is minus B12, of course. 0, I won't bother writing the things below the diagonal here. You just get us confused. 0, and then B23 over here. The other ones are simply minus these. For reasons that are historical, the components of the antisymmetric tensor are related to the vector components by an extra minus sign. This is not a cross product, but it is just a definition. This is equal to 0, 0, 0. Instead of B12 being B3, it's minus B3. Then plus B2 over here, and minus B1 over here. It's just a semi-historical glitch. There's actually some better reason for it. But of course, if a thing is a vector, so is the minus of it. And so the connection between the antisymmetric tensor and the vector that describes it is of course ambiguous. Do I describe this plane here as that vector or that vector? There's an ambiguity. Once I fix that vector, we usually fix it with a right-hand rule. A cross B, C, by making right-handed coordinates. But there was always an ambiguity whether we identify the tensor with the vector components or with minus the vector components. And for the magnetic field, as I said, just as a matter of history, they were identified with minus the components of the tensor. In other words, the opposite rule. Okay, so that's the magnetic field can be represented either as a vector or an antisymmetric tensor. What I want to show you is an interesting little theorem. The force on a charged particle is V cross B. Now, we can write V cross B we can write the components of the cross product V cross B either by thinking of B as a vector or a tensor. Let me show you what happens in the two cases. Let's work out the components of V cross B. All right, I'm only going to work out the x component of it. All right, what's the x component of V cross, or let's take the z component. Let's take the third component of V cross B. Okay, the third component of V cross B is, by the definition of the cross product, where is it? The definition of the cross product, the third component is V1 B2 minus V2 B1. Okay? That's the third component. We could write down the others just by cycling through. I'm not going to cycle through. But now let's use that identification up at the top of the blackboard to rewrite this. Notice what B2 is. It's also B13. So this is also V1 B13. What about, now there's minus V2, and what is B1? B1 is minus B23. Minus B23, so that'll change a sign here, and it'll multiply it by B23. So the component of V cross B in the third direction is V1 B13 plus V2 B23, and I'm going to add in another term, V3 B33. Why am I allowed to add that in? Because B33 is 0. B33 is 0. It's a diagonal term here. And now we have another way of expressing, a very pretty nice way of expressing the components of V cross B. All right, we can cycle through it, as I said, but we can also write it in the following way. V cross B, the mth component of it, m is 1, 2, or 3. Notice the 3 here goes with the second component of B in each case here. Look at the structure of it. In each term, you have the third component of the vector being identified with the last component of B. All right, so that suggests that we should write down here something B something M. We should write a velocity. But notice that the velocity components match with the first component of B. The velocity component matches with the first component of B, and so that suggests that the answer is NMVN. Now, this means summed over N. So this means V1 B1M plus V2 B2M plus V3 B3M. Right. Repeated indices get summed over. That's kind of a nice, easy way to write V cross B. That's what it is. That's another way of writing the Lorentz force law here. If I write it out in terms of components, then at least let's concentrate on the magnetic piece of it. The mth component of the force evidently then is electric charge Vn BNM. Okay. Keep that in mind. Let me show you another little mathematical fact about particles moving in magnetic fields. Let's forget the electric field. No electric field for the moment, just pure magnetic field. Then there's a fact about particles moving in magnetic field that their speed doesn't change. Speed is the magnitude of the velocity. Magnitude of velocity doesn't change in a magnetic field. That's because the force is perpendicular to the velocity. But let's see if we can prove that. Let's see if we can prove that the velocity, not the velocity, the speed. Velocity means direction and magnitude, but that the magnitude of the velocity doesn't change. In fact, as a consequence of that, oh, if the field varies in time, yes. A static magnetic field, yes, that's correct. Yeah.
The M subscript on F over there corresponds to the M subscript on E, right? But you also want a second subscript to denote it's only the magnetic component?
We're talking about this?
Yeah.
Everything is three-dimensional. There's no electric component in here now, but I've set the electric field equal to 0. Yeah. I've set the electric field equal to 0. If there's a time-dependent magnetic field, the reason that the velocity, the speed changes, because a time-dependent magnetic field makes an electric field. But let's just concentrate on a time-independent, simplest situation, time-independent magnetic field. We'll see, I don't know, as we go along, we'll find out if it was important that it was time-independent. All right, so among other things, that means that the kinetic energy of the particle doesn't change if it's only in a static magnetic field. That means that the square of the velocity, we can write that as Vm. The square of the velocity, this is V1 squared plus V2 squared plus V3 squared, or better yet, Vx squared plus Vy squared plus Vz squared. This is the square of the magnitude of the velocity. And I'm interested in finding out whether that changes with time. So what do I want to do? I want to differentiate it with respect to time. Remember that I sum over repeated index. All right, well, what is this? This is just twice the time derivative of Vm times Vm. This is Vm squared. The time derivative is twice V times the time derivative of V. All right? Which is twice the acceleration. Twice the acceleration dotted with the velocity. Okay. Now let's write the fact that the acceleration, we know what the acceleration is. The acceleration is just the force divided by the mass. Let's see, what do we want to do? Yeah, we want to substitute for the acceleration. I want to substitute the force divided by the mass, but in particular, I don't care about the numerical coefficients. This is going to be proportional to twice, now, velocity cross b, the mth component, times Vm. The acceleration in a magnetic field is proportional to the velocity cross the magnetic field, the mth component of it, times Vm. But now let's use the formula that we have. Where is it? The formula that we have for V cross B. Did I erase that? Darn it, I erased it. Twice B, what is it? B, N, M. Anybody have it written down? V cross B, the mth component of it. What is it?
Isn't it V, N, B, N, M?
V,
N.
N, B, N, M, right? All right, that's V cross B in the M direction. But now let's multiply it by Vm. So what do we have? We have the components of the tensor B bracketed by the components of the vector V on both sides. Now the trick is to realize that any expression like this is always 0 if B is antisymmetric. For example, there's going to be a term which will be, well, let's see what terms there are. There could be a term with V1 over here and V1 over here. That will have to multiply B1, 1. That's 0. Let's try another term. There'll be a term V1 over here and V2 over here. That will multiply B1, 2. But then there will be a partner, a twin term that goes with it, in which this is 2, in which n is 2 and m is 1. So that will be plus v2 b21 v1. And now we use the fact that b21 and b12 are opposite in sign, equal and opposite, and this is also 0. So if we take a antisymmetric tensor and we multiply it from both sides on both of its indices by the same vector, we always get 0. The consequence is that we proved that for a magnetic field that d by dt of the square of the velocity is equal to 0. In other words, that the square of the velocity is constant in time. Anybody want me to go over that again? All right, I'll just go over it very briefly again. Vm, we differentiated it and we got it proportional to the product of the acceleration times the velocity. Then I used for the acceleration the Lorentz force law, the magnetic piece of it. Of course, this would not be true, incidentally, if there was electric field. Only because if there's only magnetic field, then the acceleration is proportional to v cross b. I then used that v cross b was vnm, vn, bnm, vm. And then immediately from that, it follows immediately the symmetry of vnm is combines together with the antisymmetry of bnm to give 0. Now, why do I do it this way? I could use elementary theorems about cross products and so forth. I do it this way because we want to generalize it to 4 dimensions, where the simple theorems don't generalize. Okay. So now we know some things. Oh, incidentally, well, it's just true that, of course, that an electric field will violate this. If a particle is at rest and starts at rest, the electric field will start to accelerate it. And, of course, the velocity will not remain, the speed won't remain constant. It's only because the velocity appears in here in a particular special way that it has this property that it doesn't change the magnitude of the velocity. I don't think in any place here that I used the fact that the magnetic field was constant in time. I don't think I did. What is true is a time-dependent magnetic field will create an electric field, and the electric field will do some work. All right, now it's more or less obvious that the electric field and the magnetic field will get mixed up with each other when you go from frame to frame which are moving with relative velocity. It's fairly easy to see. This is under the assumption that the laws of physics are the same in every reference frame. It's more or less obvious that if you have a pure magnetic field in one frame, then in other frames you will also have an electric field. In other words, if there's a pure magnetic field along some axis and you're moving in some direction, depending on the direction you're moving in, you will see also an electric field. The way to see that, let's take a case. Let's suppose there's a magnetic field in the up direction that I have a particle, let's see, I have a particle which is moving with velocity v. We'll call this the y direction, the x direction, and this is the third direction, the z direction. 1, 2, and 3. We have a magnetic field in the y direction. We have a particle moving along the x direction. And of course, in that case, we will have a force along the z-axis. V cross B will be along the z-axis, and there will be a force on that particle along the z-axis. Now, let's imagine slow velocities, Newtonian physics, We're not interested in relativity yet. Everything is moving very slowly by comparison with the speed of light. Acceleration in Newtonian kinematics is invariant. So if one observer sees an acceleration, a second observer will also see an acceleration, and the acceleration will be identical as long as we're talking about observers who are moving slowly relative to each other. All right, now I haven't introduced a second observer yet. I've only introduced the fact that my particle is moving along with velocity v. But now I'm going to introduce a second observer. The second observer also happens to be moving along with velocity v, and therefore sees the particle at rest. For that observer, the particle has no velocity, but because acceleration is an invariant under usual Newtonian physics, that observer must also see an acceleration for this particle. There's no velocity, therefore the B field cannot create any acceleration momentarily. Momentarily, at that instant of time, the acceleration is 0 in one frame, it's 0 in every frame. So, as I move along with the particle, I have to blame the acceleration on something else. It cannot be blamed on the cross product of the velocity and the magnetic field. In fact, we know there's a force along the z-axis. There's only one place that could be coming from, assuming that the Lorentz force law is the same in every reference frame. If it's not coming from V cross B, because in my new frame V is 0, it must be coming from an electric field, and so there must be an electric field sticking out of the blackboard in the frame of reference moving with the particle in this particular case. So in the original frame of reference, I started with no electric field, but a particle moving with velocity v. In the second frame of reference, I have a particle at rest. I must have an electric field sticking out of the blackboard. So the consequences are that electric and magnetic fields must mix up with each other under velocity transformations. But in order to get the equations really relativistically correct, we're going to have to work with 4 vectors. So let's remind ourselves about 4 vectors and how the electric and magnetic fields fit into a 4-vector notation, and then see if we can derive a set of equations of motion which will be the same in every reference frame. And as I said, we will have to mix up electric and magnetic fields. They will have to transform. We'll work out some of their transformation properties. I mean, here we did a little bit of it, but we'll work it out mathematically and see, for example, that this really does happen. Okay. We have 2 fields, electric and magnetic. That's 6 components altogether. A second object which has 6 components. In fact, the only object which has, I say this all the time, the only object in 4-dimensional space which has 6 components is an antisymmetric tensor. Now, it's simply false. You could have 6 scalars. You could have a vector and 2 scalars. I think that's all. A vector and 2 scalars. 6 scalars, but though neither of those are interesting. The other object which has 6 independent components is the antisymmetric tensor. So it's natural, since electric and magnetic fields will transform into each other, to guess that they fill out an antisymmetric tensor in 4 dimensions. So here's the matrix associated with it. Let's, just to guide my eye, I'm going to divide it into 4 by 4. And now my notation seems to differ from a lot of books. My notation is always 0, 1, 2, 3. No, 1, 2, 3, 0. That's because in my youth I used to call 0, 4. Now it's called 0. Well, I'm not that old, but 1, 2, 3, 0. So 1, 2, 3, 0, 1, 2, 3, 0. Let's fill it in with electric and magnetic fields. And some of this, of course, is convention. Some of this is rather arbitrary convention. What the invariant fact is that there's an antisymmetric tensor that describes all of this. Exactly how we fill in the components is a little bit arbitrary, not very, but we fill in the 1, 2, 3, the 3 by 3 matrix exactly as we did with the magnetic field before. 0, 0, 0, minus BZ or B3, I think this is plus B2 minus B1. So this part of it, let me block it out. The 3 by 3 part of it, 1, 2, 3, is exactly just the magnetic field tensor. On the off-diagonal places over here, we have the electric field. We have room for the components of an electric field. I think it's E1, E2, E3. The 3 components of the electric field. And of course, in the lower spots here, we simply reverse the sign. Plus B3, for example. Down here, we would have minus E3, etc. Antisymmetric tensor, 6 independent components constituting the electromagnetic field tensor.
When you use superscripts,
Oh, as long as I'm only interested in components 1, 2, and 3, as long as I'm labeling things with 1, 2, and 3, it doesn't matter if they're upper or lower. Here, I simply mean, you're right, I switch notation up and down. Pay no attention to it. Let's see, what would be consistent? I guess it would be consistent to leave them as upper components, but it doesn't matter. It's the 3 components of the electric field and the 3 components of the magnetic field exactly as Maxwell and Faraday would have defined them. That's what go into those places there. So we needn't pay much attention to where the indices are. This is the object made up out of exactly the same fields that Maxwell and Faraday would have defined. And this whole object is called F mu nu. It's an antisymmetric 4 by 4 tensor. Mu and nu run from 0 to 4 to 3, or 3 to 0. And it is a 4 by 4 tensor. It's called F. I'm not sure why it's called F. I think maybe for Faraday, but I'm not sure. I don't think it was called F until maybe Minkowski. I'm not sure. Einstein did not have that notation. He actually didn't think about 4 by 4 tensors. What he simply worked out in detail was the transformation properties of the electric and magnetic field. I think it was Minkowski who first put them together into a tensor. All right, let's come now. That's our object. That's our electric and magnetic tensor. It's the thing that has to be responsible one way or another for the force on charged particles. Now what we want to do is study possible, excuse me, possible force laws that would be appropriate in the special theory of relativity. So let's begin with the idea of acceleration. We've already defined for velocity. For velocity, u mu is equal to dx mu by, not by dt, but by d tau. Okay. It has 4 components. What are those 4 components? They are the 4 components of ordinary velocity times gamma. Gamma equals 1 divided by the square root of 1 minus v squared. Vx, Vy, and Vz times gamma. And then the last component is just gamma. Another way to write them is dx by dt, dt by d tau. That's where the gamma comes from. The gamma is just dt by d tau. Okay, so those are the four components of force velocity. The momentum is m times u mu. That's p mu. And the first three components of it are the ordinary momentum. They are the momentum, but notice that they're made up out of mass times proper velocity. That's what goes into the generalization of Newton's equations. And it goes in not in the form dp by dt, but dp by d tau. Why? Because we want to make a 4-vector. If x is a 4-vector and tau is a scalar, and tau is a scalar, or an invariant, then dx by d tau is also a 4-vector, p is a 4-vector, and dp by d tau is a 4-vector. That's the left-hand side. In other words, it's entirely analogous to what we place in Newton's equations here, except that it's d by d tau instead of d by dt. Okay? We can write that if we like. Well, let's leave it this way for the moment. Let's leave it this way. We'll write it slightly different in a little while. If the left-hand side is a 4-vector, the right-hand side must also be a 4-vector. It's got to have the electric charge in front of it. It is going to have the electric and magnetic fields in it. Let's see what kind of thing we can invent. We can invent something with... No, let's for the moment just call the right-hand side f script f mu. F mu. Okay. Now let me prove a little theorem. The theorem is that f mu, here's the statement, f mu u mu is equal to 0. Now this is analogous, but not identical to, it's analogous to the statement that the force due to a magnetic field is perpendicular to the velocity. That the force due to the magnetic field is perpendicular to the velocity. Right? It's analogous to that. It's a 4-dimensional version of it, and we're going to see now how it works. How do we prove this? We prove it not by using any special form for f, but by using the fact, which I probably mentioned last time. If I haven't, I'll review it. Well, I won't review it. I'll do it. U mu is equal to 1. Did we do that?
Yeah.
I think we did. It's, let me just briefly remind you, it just says that the x mu by d tau, the x mu by d tau is equal to 1. And all it really says is that, well, this one of these should be lower, the x mu. All it really says is that the sum of the squares of these differentials is just d tau squared. Okay? I think we did that. I think we may have done it twice already. U sub mu times mu super mu is equal to 1. Now let me differentiate that with respect to tau. If it's equal to 1, that means it doesn't change along the trajectory of the particle. It's very much, or very analogous to the statement that the speed doesn't change in a magnetic field. Not the same thing because there's 4 components here, but it's mathematically analogous. Let's differentiate it with respect to tau. All right, we're going to get 2 terms. When I differentiate a product, I get one term from the derivative of the first factor times the second factor and so forth. So there will be, for example, du mu times u super mu. And there will also be plus u sub mu. My mu's and u's look the same, don't they? I don't want them to. U sub mu times du super mu by dt by d tau. But these are the same thing. It doesn't matter if you have, when you put two vectors together like this and sum over the indices, it doesn't matter which one has the upper index and which one has the lower index. That's entirely no content in that. So this is really just twice this. What is this object? This is twice the proper acceleration times the proper velocity. Okay? This is the proper acceleration here, and this is the proper velocity. The proper acceleration, of course, is proportional, apart from a factor of mass, it's equal to dp mu by d tau. So this is just m times the proper acceleration. All right? So what's on the left here, apart from a factor of m, is d mu du by d tau. And if I multiply it by u mu on the right-hand side, it must be equal to 0. So it follows that f mu times u sub mu must equal 0. Okay. Oh, we didn't finish this. I should have said this is equal to 0. It's equal to 0 because the right-hand side is just 1, and when you differentiate 1, you just get 0. The right-hand side is a constant. When you differentiate a constant, you get 0. And what is the expression here? It's just proportional to the force times the velocity, what I wrote up here. So you can see that f mu times u mu must equal 0. This is a kinematic fact. This doesn't depend on anything. It just depends on the definition of for velocity, for momentum, for acceleration, four-dimensional acceleration, and so forth. And so it tells us that in a four-dimensional sense, the force on an object must be perpendicular or orthogonal to the for velocity in this sense, that has to be equal to 0. That means we can't just stick in any old thing for force. It's got to satisfy this relationship here. How do we satisfy it? Well, it's, as I said, quite similar to the fact that the magnetic force is perpendicular to ordinary velocity. We satisfied that by a trick. We made the trick of making the magnetic field into a tensor, Mn, and multiplying it by Vn. This is V cross B. Then when I dotted it into Vm, it was automatically 0. Exactly the same trick. Exactly the same trick. We take f mu to be f mu nu, the antisymmetric tensor, times the for velocity. Everybody know what I mean when I put a lower index on the for velocity. It just means lowering the index by changing the sign of the space components. All right? So if I invent an antisymmetric tensor to put here, and I multiply it by u nu, guess what? If I now multiply it by u mu, the answer will be 0, because f is antisymmetric. Let's just write it out explicitly. If the force is proportional to f mu nu times u nu, and I dot it into u mu, the answer will be 0 because f is antisymmetric. So this is one way, it's only one way of satisfying the criteria that the force is when multiplied by the velocity is equal to 0, is to build the force out of an antisymmetric tensor. In fact, it's the simplest way. Well, we have an antisymmetric tensor. In fact, we even call it f mu nu, and it's built up out of the electric and magnetic fields. So let's see, let's take this apart. Here is our equation. Let's get rid of the intermediate step here. This is Q times F mu nu times U nu. And let's look at this for slow velocities first. Let's first look at it for slow velocities. We can study it for larger velocities later. But let's check that for low velocities, this really is the Lorentz force law. Let's see how it's related to the Lorentz force law. First of all, Q, that just goes for free. That's just the electric charge. F mu nu is going to involve two terms, electric and magnetic. And U has two kinds of terms, the time component and the space components of U. So let's work out some examples. Let's work out dp, which one did I work out? Yeah. Let's work out dpx by d tau. Now, the first thing is, as long as we're moving slow, I'm going to come back in a little while and discuss what happens when we're moving faster. As long as we're moving slowly, t and tau are the same. For slow motion, dt and d tau are the same. So in the non-relativistic limit, we can just take this to be dp by dt. As I said, we'll do better in a moment. I just want to make sure that for slow motion, we have all the right things. That's equal to Q. Okay, now let's see what we have. Mu and mu match here and here. So this has to be Fx, and then nu can be any one of four terms, any one of four entries there. There's first of all ffx, xx, ux. That's not there because fxx is 0. So this is gone. Then there's fxy, uy, plus fxz, uz, plus fx naught, or time, u naught. Okay, let's pull them apart. What is fx0? Fx0 is electric field. If one of the indices is 0 and the other one is space, then this is just the electric field. So this here is, we first of all have a term which is Q times the electric field. They're both x components, so this is the x component of the electric field. All right. But what are these? xy and the xz components, those are magnetic fields. So let's see what we have. fxy, that's F12. What is F12? F12 is minus B3. So this will be Q times uy B3 with a minus sign. And then from here, what is fxz? That's B2. No, that's, yes, that's B2. So this will be plus U3 B2. You see what we're getting? We're getting the cross product of the velocity with the magnetic field. To the extent that we can say that U is the same as V, we've reproduced the force law of Lorentz. V cross B plus Q times E. You see where they come from. Let's be a little more careful. Let's write it more carefully and not do the non-relativistic limit. Let's do it more carefully. First of all, we have dp mu by d tau. That is dp mu by dt times gamma, times dt by d tau. And dt by d tau, let me just write down what gamma is. Gamma is square root of 1 minus v squared, where v is the velocity of the particle, ordinary velocity. So this is dp by dt times gamma. Let's see what's on the right-hand side. On the right-hand side, we have things like, let's take this term here, q fxy uy. But uy is the same as vy times gamma. Likewise, likewise for all the terms, uy, uz, and u0. Let's see, we have q, fxy, vy. In other words, this is going to be v cross b times gamma. And the last term is just electric field times u naught, and u naught is just gamma. From the u's here. The u's are v's times gamma. And the last one here is just gamma. Right? Okay, so the gammas cancel. And guess what? We get exactly what Lorentz had. Except there's something slightly different, and that's that P is not m times V, but it's m times U. So there is a hidden gamma in here. The relativity is hidden in the definition of gamma. We can really write this as d by dt, not of mv, but of mv times gamma. Gamma changes along the trajectory, and so gamma is not a constant, but it is dp by dt. So it looks exactly like Lorentz, with the exception that we have to calculate p in the right way, as proper, in terms of proper velocity. So we've reproduced.
In the first line on the bottom board, isn't that the q times z?
Yeah. Good. Okay. Absolutely. Okay, that is the Lorentz force law as derived by, and the logic was nice. The logic was nice. We first proved that the acceleration and the velocity are orthogonal in the four-dimensional sense. That told us that the force is orthogonal to the velocity. The only simple way to do that is to build the force out of an antisymmetric tensor so that when we dot it back into the velocity, we get 0. And then we just worked it out. We just worked it out, making the identifications with an older fashioned kind of notation. Right? This is just purely notation. The definition's here. This is B, this is E. When it's all put together, it simply has the simple form of a four-vector equation. Because it's an equation between four vectors on both sides, it will be the same in every reference frame. Okay.
Would you call that derivation math or physics?
Look, once, that's a bit of buffer frame.
Is there physics in there, or is it just?
Yeah, there's heavyweight physics in there. The heavyweight physics is that the laws of nature are the same in every reference frame. That went in, and the other thing that went in, I mean, if we're doing it, we wouldn't really derive it from nothing. There are other force laws, other kinds of force laws. We certainly had, or I certainly had in the back of my mind, that we were talking about things with electric and magnetic fields, but on the other hand, not very much was used. We used the idea that if an equation is a four-vector equation, it's the same in every reference frame. That was the most important thing. Other things we used, for example, the fact that it's a second-order differential equation. This is dx by d tau, so this is d second x by d tau squared. Why isn't it d third x by d tau squared or d fourth x? Physics goes into that. There's plenty of physics that goes into that the equations of motion are second order, which is equivalent to the statement, but it's a physical statement, it's not a mathematical statement, that in order to predict the future, you need to know the position and velocity of every particle. You don't need to know the acceleration. The equation gives you the acceleration. The equation could have been that the derivative of the acceleration is equal to the force, and then you would also need to know the acceleration in the beginning. But physics tells you that that's not, experimental physics tells you that's not correct. So it's a bit of both. I mean,
So if someone thought of this from scratch, just by analogy, eventually they'd have to go out and check it experimentally because it's physics.
well, you can call it what you want. I mean, it is what it is. It is what it is. Let's talk about the transformation properties of the electromagnetic field tensor, how it transforms. Again, as a homework assignment, I can assign you to work out the transformation properties of all of the components of the electric and magnetic fields. In particular, the transformation properties when you do a Lorentz transformation along the x-axis, when you have two observers moving relative to each other along the x-axis. I could have taken the y-axis, but it would be no different, except that x would become y. Okay. The way to think about it is to first write down the transformation law for the product of two vectors. The simplest tensor, we want to work out the transformation laws for a tensor. All tensors transform the same way. Right? So if we work out the transformation law for a simple tensor composed of a product of two vectors, you'll see, as I'll show, that that tells us everything we need to know. So for example, supposing we want to know in the primed reference frame, the primed reference frame is the one moving, let's say, to the right with velocity v. I'm prime, you're unprimed, okay, and I move to the right. Let me just write down for you, to remind you, the transformation laws of the coordinates. And let's call them x1, which is what I usually call x prime, is equal to x, which is x1, minus vt, which is minus vx naught, divided by square root of 1 minus v squared. X naught prime, this is t prime, is equal to is equal to 1, which is equal to x naught minus vx1 divided by square root of 1 minus v squared. And what about x2 and x3? x2 prime is equal to x2. These are y and z. This is the transformation property for all vectors. All vectors transform the same way. All right? So now let's work out the transformation property of a tensor. Let's, for example, take two vectors. Let's make a tensor out of two vectors, a and b. All right? In other words, a mu, b nu. Let's concentrate on the first component of the electric field, the second component of the electric field. Which one do I want? No, the first component of the electric field. In the primed reference frame. Now, what is Ex? Ex is really F naught 1 prime. I'm trying to find F naught 1 prime, assuming that I know things in the unprimed frame. Now, F naught prime is like, I'm going to write not equal, but is sort of like the product of two vectors, a naught, b1. This would also be a component of a tensor. In fact, it would be the naught 1 component of a tensor. So 1 does not mean prime here. Let's calculate a naught b1 prime. How do we do that? Well, we know what A naught prime is. Here's how the naught component of a vector changes. We know what the 1 component of the vector, how it changes. So all we have to do is substitute. Let's substitute. What is A naught prime? A naught prime is built out of A naught and A1 the same way that X naught prime is built out of the components X naught and X1. Let's see if we can guess what it is. A naught prime is going to be A naught minus VA1, sorry, I better put the indices in the right place. A naught VA1 divided by square root of 1 minus V squared. That's A naught prime. Now what about B1 prime? B1 prime, we have to see how the first components of vectors change. That's going to be B1 minus V B naught divided by square root of 1 minus V squared. Does everybody see what I've done? I've said that EX is a component of a tensor, the naught 1 component of the tensor. Just as an exercise, I'm going to calculate how a similar tensor, namely A mu B nu, transforms. I'm going to see what happens to the naught 1 component of it in the primed frame. To do that, all I have to do is substitute in the naught component, the prime naught component, that I get from this equation over here. The 1 component of the primed B, that I get from this equation over here. That's these two factors. Is that clear? Anybody not follow it? Good. All right, now let's multiply them together and see what we get. First of all, we're going to get 1 divided by 1 minus V squared. That's the easy thing. Just multiply these two together. Now, next we get A naught B1. That's a component of the corresponding tensor in the unprimed reference frame. We'll use that. Now we get minus V A1 B1 minus V A naught B naught. That comes from the A naught B naught term here and the A1 B1 term here. And finally, plus V squared A1 B naught. Now, the only unusual thing about F is that it's antisymmetric. We could guess now what the transformation property of F naught 1 is. Let's make the guess. F naught 1 prime is equal to F naught 1, that's from here, minus V F11, this is F11, minus V F naught naught, plus V squared F1 naught. That's this. All divided by 1 minus V squared. Okay. I've said A times B transforms as a tensor. Here's its transformation properties. I know it just straightforwardly from the transformation properties of the two vectors. And now I identify the components of AB with the components of a tensor. This is how a tensor transforms, but an antisymmetric tensor is especially simple. F11 and F naught naught aren't there, so we can erase them. What about F naught 1 and F1 naught? They're the minus of each other. So this becomes F naught 1 times 1 minus V squared. And the whole thing is just F naught 1. Oh my goodness, it looks like F naught 1 prime is the same as F naught 1, and that's correct. What does that say? That says that if two observers are moving down the axis, and there's an electric field along the axis, okay? We're doing a Lorentz transformation along the one axis, and we're looking at the component of the field along the one axis. It says that the component of the field along the direction of relative motion is unchanged, is the same. And that's a true fact, that the component of electric field, and it's also true of the magnetic field, maybe we'll do it. It's also true of the magnetic field. In fact, the electric and magnetic field transform very similar to each other. Okay. But now let's do a case which is less trivial, where there is an interesting transformation law. Let's work out the transformation property of a component of the electric field perpendicular to the direction of motion. Well, what's the transformation of A naught? We had it worked out over here. The transformation of prime. The transformation of A naught is unprimed A naught minus VA1, again, divided by square root of 1 minus V squared. That's A naught prime. And then B2, this is, incidentally, this B here is not the magnetic field. Don't get confused. This is just two vectors, any two vectors. What is the transformation property of the second component of a vector? The y component in this case, when I transform along the x-axis. Nothing changes. So this is just B2. All right. Let's see what we have. We have A naught B2 divided by square root of 1 minus V squared. A naught B2 over square root of 1 minus V squared. Well, that suggests that we replace this by F naught 2 divided by square root of 1 minus V squared. That's the first term. And then minus V times A1 B2. That's F12. F12 divided by square root of 1 minus V squared. Okay, let's see what this says. This was the primed component E2 prime. E2 prime is equal, this is E2, minus V, now what is F12? F12 is plus or minus B3, which is it? I think it's B3, minus B3, I forgot. Minus B3? So it must be plus V B3 divided by square root of 1 minus V squared. So we see that this is E2. E2 prime does change, and it's equal to E2 plus VB3 times gamma. If the velocity is slow, then gamma is close to 1. And it just says that the electric field mixes in a little bit, the second component of the electric field mixes in with a little bit of the third component of the magnetic field. This was for a transformation along the x-axis, along the one axis. You can work out in the same way the details of all of the transformation properties of all of the components of the electric and magnetic field and find out, if you know them in one frame, the stationary frame, what they are in the other frame. Okay? In particular, you can check that if you have only a magnetic field in one frame, that if you move relative to it, you see an electric and a magnetic field. And you can work out the directions that the electric and the magnetic field will point in. And these transformation properties for the electric and magnetic field will always be such that, that the equations of motion in any frame of reference for the charged particle are the same. Okay? Okay, any questions about the charged particle in the electric and magnetic field?
If you have a current flowing through a wire,
Mhm.
you get a magnetic field. What sort of velocity do you have to go at in order to make that magnetic field equal to zero?
Zero.
Why?
To go along with that charge?
If you have current in a wire, and you've got Q's going at some V through the wire, what velocity do you have to go in order to make the B field?
Sounds like you want to keep up with the electrons.
Yeah, but is it
It's probably.
low velocity or
Is it?
real fast velocity?
Well, it's not a relativistic velocity. I mean, it's not. It's a medium velocity. Yeah, but we can work it out. We can work it out, but very slow? No, it's not that slow. To get rid of the magnetic field? No.
Well, the velocity of electrons in a wire is slow.
Yeah, the drift velocity.
What is it?
It's meters per second.
That's not the right velocity. I'm not sure why, but.
Well, electrons moving in a wire are.
Well, wait. You got to be careful. Yeah. There's positive charges there too. No, it doesn't transform that simply. I think we just have to work out the magnetic field and do it. It's something I don't know the answer to offhand. I suspect it's sort of intermediate, not too slow, not too fast. It's not very slow.
Can you ever get rid of the magnetic field?
Yeah, I think you can get. No, not if there's only a magnetic field. Not if there's only a magnetic field. You can't get rid of it. No.
Right, that's the
You
problem.
can't. But if there's an electric field and a large electric field, you might be able to get rid of the magnetic field. In other words, the transformation property of the electric field will produce a little bit of magnetic field, which could cancel the original magnetic field. If all you have is a magnetic field to begin with, no, you can't. Right? But for example, I mean, all right, so what I was thinking, which was inappropriate for the problem, but if I had a moving collection of charges, and the moving collection of charges makes a magnetic field, it also makes an electric field. If I, just a lump of charge, it's moving, it makes an electric field and it makes a magnetic field, then I can answer very quickly what velocity do I have to move with to get rid of the magnetic field. I just have to move with the object and there's no magnetic field. That the current in the wire is trickier. And the electric field cancels out from the protons and the electrons, and there's no way to get rid of it. There's no way to get rid of it. Okay.
Does the electric potential and the vector potential form a four-vector?
Yeah.
Very similar to
Yeah,
this?
form a four vector. We will also study Maxwell's equations, but before we do, we want to think a little bit about waves, scalar waves, scalar wave equations. The main point being that we haven't talked about derivatives of fields. We've talked about the object dx, which might be a little displacement along a world line. Now let's come to what apparently is an entirely different subject, a theory of fields. Let's forget now particles, let's concentrate on fields. Fields are things which vary in space-time, so they depend in general on all four components of position. Let's call phi. Phi is a field. Phi for field. It's a scalar field, which means it has only one component, the simplest possible thing we can make. And now we can differentiate it. We can differentiate it to create d phi by dx mu. This consists of four terms, or four components, d phi by dx, d phi by dy, d phi by dz, and finally d phi by dt, or d phi by dx1, d phi by dx2, d phi by dx3, and d phi by dx naught. They form a four vector, but they form the covariant components of a four vector. They transform slightly differently than the components dx mu. How do they transform? They transform the same way, not as dx mu, but as dx mu with a lower component. Let me remind you what the lower component means. The lower component simply means you change the sign of the time components. No, the sign of the space components. If d super x mu is a set of four numbers which form the contravariant components of a vector, then this object here is just minus dx1 dot 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 dx3 minus also dx2 and then dx naught. You change the space components and those things define the covariant components of the vector. It's the same geometric object just being described differently, right? Just being described in a different notation. It's useful because we can make scalars by contracting lower and upper indices. Contracting means you take a lower index and an upper index, you identify them in sum, and that makes scalars. So it's a useful device. It takes into account this extra sign in things like t squared minus x squared minus y squared minus z squared. Okay. If you were to work out the transformation properties of the derivatives, now how do you do that? You know how the x's themselves transform. You know what the coordinate transformations are. X1 prime is equal to whatever it is, all that Lorentz transformation stuff. You know how they transform. You know what combinations of the old coordinates, the new coordinates are, and you can work out. You can work out the derivatives of the same field phi with respect to x prime mu. I'm not going to do that on the blackboard. It's a little bit tedious. We could work it out and see what the connection between the derivatives with respect to the prime variables, the moving coordinates, and the coordinates of the unprimed coordinate frame are. And the answer is that they transform the same way, not as the dx mu's here, but the dx mu's with a lower index. That's fairly easy to prove. And so this object is a four vector, but it forms the covariant components of a four vector. These are the covariant components of a four vector. Is it clear what that means to everybody? Just that it transforms in that way. It forms a complex of four things. Can we make an object with upper components? Sure, we can make an object with upper components. We just change the sign of the space components and leave the sign of the time component alone. All right, so we have two sets of objects. We have d phi by dx, let's call it 1, 2, and 3, together with d phi by dx naught. And that's what we call d phi by dx mu. Now, we can also consider, and this is a definition now, d phi by dx with an upper index. Instead of the lower index, it now has an upper index, and that's just the same thing here. Let's cross this out, with a minus sign here. In other words, the object with the lower index and the upper index are related in the same way that all four vectors with upper and lower components are related. In fact, every time you differentiate an object, if you have any tensor or any vector or any scalar, and you differentiate it, let's suppose you take a vector field. Here's some vector field that depends on x. Let's suppose it has an upper index for simplicity, and you differentiate it with respect to x nu. That makes a tensor, but it makes a tensor with one upper index and one lower index. Every time the derivative operator acts, it simply puts another index on the object. All right? So if v is a vector and you differentiate it, you get a tensor. If v is a tensor and you differentiate it, you get an object with yet another index, and so forth. The differentiation always puts the index downstairs. Right? So differentiation is another rule that allows you to form vectors. Vectors, tensors, and so forth. Now what I want to discuss for the remaining time today is wave equations and the invariance of wave equations. The invariance of wave equations follows if the wave equation has the form that some scalar is equal to 0. Scalars are the same in every reference frame. And so if we can write the equation for some wave in the form a scalar is equal to 0, then we can be sure it's the same in every reference frame. In other words, if we coordinate transform things. Let's try to do that. Wave equations, by their very nature, incidentally, always have two derivatives, not one derivative. They correspond to second derivatives acting on fields. Of course, we could imagine wave equations with 6 derivatives, but the simplest wave equations, Maxwell's equations, other wave equations, have second derivatives in them. That means that we're going to have a derivative and another derivative acting on some field equals 0. This is a typical example of a wave equation. There are other wave equations, but let's look for one like that. We want it to be the same in every reference frame. So that means we want it to be, the left-hand side to be a scalar. Right? Left-hand side to be a scalar would be a one way of going to make a wave equation, a single wave equation. All right? There's only one way to do it. There's really only one way to do it, and that's we've got to begin by differentiating, so let's put mu there. The only way to make a scalar out of this is to differentiate again and to put the index here upstairs. What does it mean that the index here is upstairs? It means that the space components of the derivative are treated with a negative sign. This is the simplest wave equation. It's invariant because whenever you contract a lower index with an upper index, it automatically gives you something which is invariant under Lorentz transformations. So this is the simplest example of a wave equation, and let's write out what it actually means. Let's write out what it actually means in detail. Let's take first the time component. The time component is just d naught phi, and now the time components don't change sign when you raise the index. So this is just the second derivative with respect to time. The first derivatives do change sign when you raise an index, and so this is minus d second phi by dx squared, same thing for y squared, same thing for z squared. This equation, well, this is d by dt squared. This equation has the virtue of being the same in every reference frame. How do you check it? You write it in a form in which it's manifestly just a scalar, one index upstairs, one index downstairs. Okay? That always gives you a scalar. That's the simplest wave equation. The reason I'm writing it down now is because we want to get to Maxwell's equations. This is an example of a simple wave equation. Maxwell's wave equations are more complicated, but we want to get to Maxwell's equations, and we want to write them in a form which is equally manifestly Lorentz invariant. That's our goal. We're not going to do that tonight. I think we're going to quit now. Next time we'll come back and work out Maxwell's equations in a covariant notation. They're equations which mix up electric and magnetic fields in a somewhat intricate way, but they have the virtue of being written, or the way we'll write them has the virtue of being explicitly Lorentz invariant. I'm getting tired, so I think we'll quit. Any questions?
For zero rather than a constant?
What's that?
Why does the scalar have to be equal to zero?
Oh, it could be.
Constant?
No, it could be a constant. In fact, it could be any number of things. It could be any scalar on the right-hand side. This is one particular example of a wave equation. Another one which is interesting is to write a constant here times phi. All right? What's on the right-hand side? You could have constant times phi squared. You could have all kinds of things. The simplest equation is just to have 0. And we're going to discuss those equations. We're going to work them out. We're going to work them out, study their solutions, understand how they behave. But this is just the simplest example of a wave equation. And next time, we'll study them in some detail.
The preceding program was brought to you by Stanford on iTunes U and is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at itunes.stanford.edu.